to make sure that, that the mic is on. All right, guys, just gonna continue from where we left yesterday. Yesterday we started talking about image processing using CNN, the CNN, which is the convolutional neural network, which will take an image and receive the image just like human. The human will receive the image through local features. So, which means that when you're looking at an image, we usually create the whole picture based on a certain portion of the picture. So you need to completely see the picture for you to understand what it represents. So if we're looking at an animal such as a dog, we're looking at different part of the dog to confirm it is a dog, or we're looking at a cat, we can say this is not a tiger, it's a cat, because we're looking at different features or different details that we have. That's exactly what the machine is going to do. So the machine is also going to look at images and getting the details, every single detail. So in the convolutional neural network, we'll have a fully connected network. So when an image is used to be identified or to be used as data in a neural network, image is input to a fully connected neural network. Okay, so the image is expanded into a vector, which means we take the image as it is completely and find the representation in terms of a vector or spatial representation, or the spatial relationship between the pixel. And we've seen in this course how we're looking at the image, and each pixel of the image will have its own intensity and its own details, right? So when we're looking at that, CNN will look at images, and each part of the image, which is each pixel of the image, we're going to take those information, and those information are going to play a role into the neural network. Those information are going to be used as the input details in the neural network. So processing images using a fully connected network will have certain disadvantages. Yes, it has advantages of seeing details and everything, but some of the disadvantages is that in a feed-forward neural network, which is a neural network that takes information from the input to the output, we're going to have pixels that are going to be identified. So pixels for the whole image, right? So the way the computer will store and process images will result in a lot of parameters, okay? So a common feed-forward neural network cannot really resolve image invariance. So this is why we're going to have to deal with images up to a certain percentage. So the accuracy of a neural network, when we're going to use the accuracy of a neural network, is not going to just to be 100%. The accuracy is going to get to a level of what you call this percentage which will be acceptable. So when we're looking at the field, at the fully connected network, a neural network, the way it works, it takes information from the, what you call this, the input layer, hidden layers, as we've seen it previously, up to the output. But when we're looking at images, this is not going to be enough. So this is why when we introduce neural network for images, we can't just take a simple connected feed forwards neural network, but there is a certain thing that need to be done. For example, certain kernels that need to be involved, so that before we can take just the inputs based on the pixels information, we can also let the image go through a different process, such as a kernel, where we're going to have a convolutional layer where the picture goes through a kernel where we have a certain transformation happening to the images. So this is how we can obtain the structure of the convolutional neural network, which is a feed-forward neural network, which will have different components from a neural and from a normal neural network. Okay, so the CNN is great for image processing. It will consist of a convolutional layer. We're going to have a pooling layer and a fully connected layer. So we don't just look at the fully connected layer, but we're going to have a convolutional layer where we're going to have a convolutional kernel. We're going to have a pooling layer and a fully connected layer. So with a CNN, there is no need for complex image pre-processing, like really changing a lot of things on the images, because the CNN is going to help us, especially with different layers. So a CNS can take raw image input, which is one of the reasons why they are popular. So the CNN are popular because we don't have to go through the pre-processing of images. So we can take the image, we have the input image here. So it goes through a convolutional kernel, which will map the image into a feature images, right? And then we have pooling layers and a fully connected layer. So that's how the CNN is going to work. So, so this is an example of how a single convolutional kernel calculation happens. So this is the image that we have. I hope you guys understand what are these numbers. Can anybody tell us what are these numbers? Can anybody tell us what are these numbers? Guys, can anybody tell us what are these numbers? What are these numbers coming from? What is the size of this picture? What is the size of this picture? Anyone?
It's a 5x5.
Yeah, this is a 5x5. So these numbers are details about the pixels at each pixel, the intensity that we had, as we've previously seen it in previous lessons. Guys, I will encourage that if you miss a lesson, go back to the recording and watch, so that we're moving together. So, because if you are confused at this level, it means you've missed these lessons. Okay, so this is a 5x5 pixel, and then we introduce a filter which will do the calculation. This filter is a 3D, and this filter is going to apply to each group of 3x3, and that's to obtain uh, informations, uh, to obtain this information. Uh, so this is how this is going to work. So we have to obtain, so we have this 5x5 that will be converted into a 3x3 here by applying a 3x3 kernel. So this 3x3 kernel or filter, what it's going to do, you take this 3 here, it's going to multiply by the 3. So basically to obtain this number here, 5, to obtain this 5 here, this number, so we're going to apply the kernel here in the first one. The first part is going to obtain that -5, and then we move it. The second part is going to obtain that middle. So to obtain that middle, that means here we're going to have -1 times -1 plus 0 plus 0 plus 1 times 2 plus -5 times that. And then when we add those numbers that we're going to have, we're going to end up with that 0 there. So that's how the single convolutional kernel will actually work. So we're looking at now when we have multi-convolutional kernel calculations. So this is the input image that we have here. So we can have multiple kernel. That means the first kernel that we have, the first one is a 553. That means we have this one, and then we can get a feature of the feature map. Okay, so multi-kernel convolutional will take layers. So a multi-kernel convolutional layer extracts the local image feature by using multiple convolutional kernels. So that's how the image is going to be converted into what we have. So this is what we have for like the input image pixels. We're going to extract the edges, textures, and then have an idea on the local features. And then we can have the target features, which will be that as an example. Yeah. Okay, and then from the convolutional layer, we have the pooling layer. So the pooling layer, we're going to have a maximum pooling or an average pooling. Okay, um, so the maximum pooling, which means that on that portion of the picture, we're going to get the maximum of the pixel value, which will be used for that area. So that's how that's how the kernel is going to work when it comes to pooling. So pooling will reduce the numbers of parameters while keeping the most prominent features. So this will help reduce overfitting and expands the receptive field, right? So this is an example of a picture which went through the maximum pooling. That's how we went from this to this. So we have more, the picture has been transformed to a format where we have more details. Okay, so the maximum pooling, this is an example of a maximum pooling. That means look at these details about the pictures. So when you apply the kernel to do a maximum pooling, like here we have a 2x2 kernel size. So a 2x2 will take this 2x2. Here the maximum here will be 2. So that will go there. And then here the green one, the maximum is 7. we have 7 here, and here on the blue, the biggest number is 4. So this is what the kernel is going to do here. It's 9. So this is the maximum pooling. But when we apply the average pooling, so with the same kernel size of 2 by 2, so we're going to have the average here, which is 2 plus 2 plus 1 plus 1 divided by 4, which is 1.5, and then the average here is 5. So we're actually calculating the average there. So so this is what we have for pooling. So we can have a maximum pooling or an average pooling. So those are the 2 pooling methods. And after the convolutional layer, we also spoke about the pooling layer, and then the last layer in the convolutional neural network will be the fully connected. So the fully connected layer can map and obtain the features onto separable space, all right? So the fully connected layer is the one that is going to act or to serve as a classifier for the entire convolutional neural network. So it's going to serve to actually determine what's the identity of the object. So from the input to the output. So that's what say the fully connected layer. So from the input, maybe when we take the input, we had a certain amount of data, and then the output will determine what class we're talking about. So if it's a picture, maybe of animals, so after the fully connected layer, then it's going to tell us this is a cat or this is a dog. So the core idea of CNN is the local perception. So when we talk about local perception, it means that we based on each pixel, the information of each pixel. So pixels in the same area, the relationship between those pixels will tell us what are we talking about. So when we're looking at CNN will look at each pixel and get information about each pixel. And now the more we get information about all the pixels, the machine can be able to create a pattern and understand the relationship between these pixels to form the complete image. So that's why we say so. The same way human being also work. You know, when you're looking at someone coming there, you can't recognize the person. You're looking at the image of the person, you can see the eyes. You like to know these eyes look like John. And then the more information you're having, the more details you have of the image, then you can identify who was that person, if it was really John or it was someone else. Okay, so the idea of CNN of having this system of looking at images from a local perception. So each neuron only needs to collect information in the local receptive fields. That means that when you're looking at the input layer, so this is the input layer. So if we have this image, if the size of this image is maybe 28 by 28. If the size is 28 by 28, that means the input layer will have 28 times 28, which is 784 input layers. And each node, 788 input node, and each node will have information about each pixel. So now, to be realistic, we have, let's say this picture is a 1000 by 1000. it means we have 1,000 times 1,000, which is 1 million nodes in the input layer. And each node will have an information of 1 pixel. The correlation between those nodes, those pixels, will form the fully the full image. All right, so you need to understand now. We're going to have this 1 million hidden information pixels coming, and then if you apply a filter of maybe 10 by 10, you now have 100 million parameters. So this is how CNN is really advanced, because of the amount of details that it's going to have on the picture. Because imagine now you're dealing with 100 million parameters, and the machine has to actually learn from all that. So yes, there's a lot of computation happening, but it's give you more accuracy. That's why CNN is the best neural network for image recognition. So so to get this implementation in the CNN, we need to keep the kernel far smaller than the inputs image. Remember, so here the input image is a 1,000 by 1,000, but the kernel is only 10 by 10. You can't take a kernel of 1,000 by 1,000, or else you're going to have an explosion of the details here. So because the kernel is all about reducing the size thing. So so in this case, we have the source pixel. This is the source pixel here. We apply a convolutional kernel here, which is a 3 by 3 to this image, which is going to map this. All right, so all right, so and then we can have what we call an image invariance. So okay, so this is in the case where you look at an image, you have a certain shape, right, which is located anywhere in the image. So it doesn't matter where we have that. So let's say we have two different images, but in that image you find the same shape, right? So in the first data, you have a certain shape which is here. In this image, it's on a different places, right? On a different place. No matter where this shape is, when you take the data, because it's going to take all the pixels for everything. So if this is the image that we have, let's say this was you writing number 7, and this is number 7 is written, this one is written at the bottom of the page, this one is written in the middle. The machine is still going to take each pixel and it's still going to map it to get to a point where you're still going to get the same output. So that the one of the advantages of CNN, the accuracy it has, you understand? So so that's the advantage with CNN. So we have translation invariance, so less compute and memory capacity needed. To implement that, we use the same kernel to scan the entire image. So remember, when we're using those kernel, it's need to be the same kernel. Don't change. It can't change during the image. So for the same image, we're using the same kernel. So this is how the machine can learn from images that look like this and look like this, and still get to create an identity of a cat and be able to identify cat, even if cat can the picture that you provide, the cat is looking on a different side. Okay, so it can still be able to identify them. Okay, so these are example of a full neural network. You have an input layer where all the information about the image will be. Then there's a convolutional layer that is applied, which reduces the image. And then we have the maximum pooling, which is applied here. And then on the result of this maximum pooling, there's another kernel which is applied convolutional, you know what I'm saying? So that you can have as many as you can. And then in the end, you have now the fully connected layer. And then you use an activation function, which is the softmax. You can be able to find the output. So if the whole purpose of this study was to have data separated, maybe pictures of people separated into male and female, in the end, we're going to have two categories, two outputs, which is one will represent male, one will represent female, and the output will just be probabilities. All right. So so we now have we've had so much development in terms of deep learning. As years go by, there's new technologies coming in. There's new structures that are being implemented in terms of bringing pre-trained models. So we can have pre-trained models that are already, sometimes you don't have to recreate the neural network for image classification. You can just implement a pre-trained model out there. So as you are using the neural network, it's very important to make sure you are using the right activation function. Remember, we talked about the ReLU, that's it's an activation function which does not have a gradient vanishing. So yeah, that's very important. So this is the AlexNet is one of the systems that's already it's highlighted by having it's used the ReLU, okay, instead of the sigmoid activation function, and then it use overlapping pooling, and then to prevent overfitting, it will the AlexNet will randomly crops the images 256 by 256 into 224 by 224 image. It can flip them horizontally or randomly intensify the illumination. So it does what we've learned in previous lesson as data augmentation. And in terms of other parameters that can be used for to prevent overfitting, it uses a dropout, which means that it can leave a certain part of the neural network during training. Yeah. All right, guys. Okay, so and then another model that was proposed, another method that was proposed for convolutional neural network is the VGGNet, which was proposed by the Visual Geometric Group of Oxford University. So this model will also use multiple type of convolutional kernels, right? So when you look at the AlexNet will use sizes such as 11 by 11, 5 by 5, but this one will use several consecutive 3 by 3. Okay, so all right, so these are just some configuration of the VGGNet. Okay, so these are just examples of algorithms that are using the CNN. So you have another one created by Google, which is the Google Net. So the Google Net was just designed to illustrate the use of convolutional kernels of different sizes, wider network. This is for classification problems where we're trying to classify between different classes, when you're dealing with images. So the Google Nets will include an inception module, which use a dense structure to approximate the space CNN and illustrate by, we can see this figure here. So it's going to have, it use multiple convolutional kernel, different sizes, and combine them in order to do the whole process. Okay, so these are just examples of the calculations. All right, I think that will be all for today. Yeah, any question before we call it a day? All right, guys. Thanks. Have a great weekend. I will see you in the next lesson on Tuesday. Please don't forget to go through all the recordings that you may have missed so that we are always on